Hello everyone, this is my name is Sanjay Khadanga and this is my project bike sharing demand prediction, and those are my team members Vibhushan Sahu and Balram Pranigai. So let's start our project. Sorry. So this is the our content of our this whole project. This is the first our business understanding, data summary, feature analysis, exploratory data analysis, data prepare processing, implementing algorithms, challenges and conclusions. Lastly, if I talk about first business understanding, then bike rentals have become a popular service in recent years, and it seems people are using it more often with relatively cheaper rates and ease of pickup and drop at own convenience is what making this business thrive. Mostly used by people having no personal vehicles and also to avoid congested public transport, which that's why they prefer rental bikes. Therefore, the business to thrive and profit more, it has to be always ready and supply number of bikes at different locations to fulfill the demand. Our project goal is a pre-planned set of bike counts values that can be handy solution to meet all the demands. So next is our data summary. This is the last 5 rows of our data. And in this data set, we have 8,660 lines, that is row, and 14 columns. There are three categorical features, that is seasons, holiday, and functioning day. One date time features are there, that is date. We have some numerical type variables such as temperature, humidity, wind, visibility, dew point temperature, solar radiation, rainfall, snowfall, which tells the environment condition at that particular hour of the day. And this is the brief summary of our features. And next is our insight. What is, we get the insight first instead of our data set, that is there is no missing value and duplicate value and null value present in our data sets. And finally, we have a targeted variable, that is rented by count variable, which we need to predict for new observations. The dataset shows hourly rental data for 1 year, that is 1st December 2017 to 31st November 2018, that is whole 365 days. And we consider this is a single year data. So we convert the date column into three different columns, that is year, month and day. So as it is a single year, we consider it a single year, so that's why we don't use the year column, so we drop it. And for our convenience, we change the name of some features, and this is our below. Next is our the analysis of our targeted variable, that is rental by column. And in the above graph from left side, the rented by count has moderate right skewness present, and in the right graph, that is box plot, shows that we have detect outliers in rented by column. Since the assumption of linear regression is that the distribution of dependent variable has to be normal, so we should perform square root operation to make it normal. And after performing square root operation, we get this result. In our left side, we can see that there is no skewness present in the data set, and here we get the almost normal distribution. And in the right side box plot, we can see that we find that there is no outlier present after performing the square root operation on the data set. Next is our analysis of month variable. From the above bar plot, we can clearly say that from the month of 5 to 10, the demand of the rented bike is high as compared to other months. These months comes inside the summer season. So we can clearly say that people use more rented bikes in summer season as compared to other seasons. Next is our analysis of weekdays and weekend variable. From the above point plot, we can say that in the weekdays, which represent blue color, shows that the demand of the bike higher because of the office hour. Peak time or at morning is 7 a.m. to 9 a.m. and at evening it's 5 p.m. to 7 p.m. The orange color represents the weekend days, and it shows that the demand of rented bikes are very low, especially in the morning hour. But when the evening starts from 4 p.m. to 8 p.m., the demand slightly increases. Next is our analysis of hour variable. In the above plot, which shows the use of rented bike according to the hours, and the data are from all over the year. Generally, people use rented bikes during their working hour from 7 a.m. to 9 a.m. and 5 p.m. to 7 p.m. at the evening. And next is our analysis of functioning day variable. In the above point plot, we shows the use of rented bikes in functioning day or not, and it clearly shows that people don't use rented bikes in no functioning day, and in its blue color shows that people use the people's pattern of using a rented bike is the same as the other days. Next is our analysis of season variable. In this above bar plot shows the distribution of rented bike count season wise, and we can clearly see that people love to ride bike in summer season and autumn season, but in winter season people don't take any rented bike due to because of snowfall. So here we can say that the snowfall can play a major role when a customer use a rented bike or not. Next is our analysis of season variable. This is a point plot. In the above bar plot and point plot, we can which shows the use of rented bike in 4 different seasons, and it clearly shows that in summer seasons the use of rented bike is high and peak time is 7 a.m. to 9 a.m. and 7 p.m. to 5 p.m. in evening. In winter season, the use of rented bike is very low because of snowfall. It also clearly shows that. And next is the analysis of holiday variable. In the above bar plot and point plot, which shows the use of rented bike in holiday, and it clearly shows that in non-holiday bike demand are normal as other day, but in holiday people use the rented bike from 2 p.m. to 8 p.m. because they want to roaming the city, and that's why they use 2 p.m. use their rented bike at 2 p.m. to 8 p.m. in non-holiday days. And this is the analysis of the all numerical variable versus rented bike count. And from this temperature plot, we can say that people like to ride bikes when it is pretty hot, around 25 degrees Celsius in average. And in dew point temperature, it is almost same as the temperature variable. There is some similarity present, and we can check it in our next step. And in our solar radiation plot, we can say that the rented bike is huge, and there is a solar when the solar radiation is high, the use of rented bike is huge. The counter of the rents is around 1,000. And in our next plot, that is snowfall. In snowfall plot, on the y-axis, the amount of rented bike is very low. When we have more than 4 centimeters of snow, the bike rents is much lower. And in rainfall plot, if it rains a lot, the demand of rent bikes is not decreasing. Here, for example, even if we have 20 mm of rain, there is a big peak of rented bikes. In wind speed plot, that the demand of rented bike is uniformly distributed despite of wind speed, but when the speed of the wind was 7 meters per second, then the demand of bike also increases. That clearly means people love to ride bikes when it's little windy. Next is these are the regression plot of all numerical variable as compared to our target variable, that is rented bike columns. And from this regression plot, we can say that all numerical feature, we see that the columns temperature, wind speed, visibility, dew point temperature, solar radiation are positively relation to the target variable, which means the rented bike count increases with increases of this feature. Rainfall, snowfall, humidity, these features are negatively related with the target variable, which means the rented bike count decreases when these features are increases. Next is our OLS regression model. Here, right side, from this table, we can say that the R square and adjusted R square are near to each other, and 40% of variance in the rented bike count is explained by this model. And in the p-value column, the p-value of dew point temperature and visibility are very high, and they are not significant as compared to other variables. And the next is our correlation matrix. This is to check the correlation between two variables. And from this heat map, we can say that variables like dew point temperature and temperature are highly correlated because the number is 0.91. It's approximately 1. So we can say that dew point temperature and temperature are almost similar. So we don't use the dew point temperature as well. Next is our the model building part. After we're doing the all the ADA process and data pre-processing process, we can perform this model, and for this we perform a 7 regression model, that is linear regression, lasso regression, ridge regression, descent tree regression, random forest regressor, gradient boosted regressor, and gradient boosting regressor with GRIDSEARCHCV. To use the hyperparameter tuning, we use the GRIDSEARCHCV in gradient boosting regressor. So after performing all this model in linear regression, we can see that in trend set results, the R square result is 0.77 and MS result is 35. After we normalize the y variable, that is our target value rented by columns, we can say that this is the R square is in trend set is 0.77 and in test set that is 0.78. So that not so bad, not so good. So and here below, this is the comparison of variable of predicted and actual variable. And in right side, the descent tree results. In trend set, that is we get the R square is 0.69, and in test result, that is R square, that is 0.64, and MAC is 46.48, and here test result, that is 55.59. And below we can get the predicted and actual value comparison. Next to the model are lasso regression. Here we get the R square 0.4 in trend set and 0.38 in test result. That very much poor this model perform as compared to other. And in ridge regression, the trend set we get the R square value 0.77 and test results is for R2, that is 0.78, and adjust square R square is 0.76 for trend result and adjusted R square 0.78 for test results. This is this regression model also not that kind of good or not that kind of poor. So in next our elastic net regression, here you can get the R square is 0.62 and test for trend result, and for test result that is R square is 0.62. Next is our random forest. So in random forest, we can after performing this model, we get the trend set result, that is R square is 0.98, and in test result that is 0.92. This is a very good regression model, we can say that. And after performing this model, we can get the feature importance variable, that is the most important feature. We can get the temperature, humidity, and function day rainfall. So you can say that temperature and humidity plays the high important role while selecting a customer is going to use a rented bike or not. And in the table, we can see that temperature impedance 0.31 and humidity impedance is 0.16. So temperature play important role. Next is our gradient boosting regressor. In trend set, we get the R square result is 0.87, and in test set we get the R square result that is 0.86. And here the right side, it is the feature importance graph, and here also we can see that temperature play an important role in deciding factor of the target variable. And in the below table, we also see that temperature play importance role of 0.32%. And next is so we decide to use a hyperparameter tuning for gradient boosting. That's why you use the GRIDSEARCHCV. So next our model is gradient boosting regressor with GRIDSEARCHCV. After performing the GRIDSEARCHCV, we get the hyperparameter, that is max depth is 8, minimum sample leaf is 40, minimum sample split is 50, and n estimator is 100. After from the basics of from these, we get the trend set we get the trend set results, that is R square is 0.95 and test result we get the R square is 0.92. That is also a good regression after performing hyperparameter tuning, and we get the feature impedance also. Here also we see that temperature, humidity plays a very much important role in our target variable. In the below table we also see that temperature play impedance role of 0.31 in the after performing with the gradient boosting with hyperparameter tuning of GRIDSEARCHCV. Next hour, so after while doing this project we have faced some challenges that the data set we handle is too large, and we need a very large amount of plots and graphs to analyze the data, and there are some challenges in feature engineering and feature selection also. And while optimizing the model, we decided the carefully tuned hyperparameter as because it affects the R2 square. So next hour, after performing all these models and ADA, we came to a conclusion of some points, and here are these. First is our hour of the day. Our columns of the day holds the most important feature. Bike rental count is mostly correlated with the time of the day, as it is peak at 10 a.m. morning and peak at 8 p.m. at evening. We observe that bike rental count is high during working days than non-working days. We see that people generally prefer to rent bike at moderate to high temperatures and when it's little windy. It is observed that highest number of bike rentals count in autumn and summer seasons and the lowest in winter season. We observe that the highest number of bike rentals on a clear day and the lowest on a snow and rainy day. We observe that with increasing humidity, the number of bike rental count also decreases. And in our next point is about the model selection. When we compare the root mean square error and mean absolute error of all the models, random forest regressor and gradient boosting with GRIDSEARCHCV gives the highest R square of 99% and 95% respectively. For trend set, it's 92%, and for test, for 99 and 95% for trend set respectively, and 92% for test each. So finally, this model is best for predicting the bike rental count on daily basis. As the environmental condition, that is snowfall, temperature, and other kind of variables don't fix for a particular time. So this model also challenging for us to build this model because it randomly changes this variable. And after summarizing the whole model, we collect all the data in a single table. You can see that. So this is our model. So any Q&A session. Thank you for being patient with me till the end. Thank you very much.